Hi, I'm going to show you how to use conservation of energy to solve electricity problems. I'm just going to dive right into the scenario. So the scenario that I'm going to be solving for is a high-speed proton. So we'll give it a speed of 1 million meters per second, is fired directly at a charged object that has, we'll call this Q1, and it has a charge of 3 microcoulombs. Okay, and let's assume that this was fired from very, very far away. That'll just make the math easier for us. And then we're going to find the distance of nearest approach. Okay, and the reason we use conservation of energy in this case is because there is a variable force. So thinking about this in terms of Coulomb's law, there would be a repulsive force pushing back on that proton as it gets closer and closer to this macroscopic charge here. And so it would be very, very difficult to use, say, Coulomb's law combined with Newton's second law in kinematics to calculate the distance of nearest approach. Okay, so the workaround, as it often is when you have a variable force, is to use conservation of energy. So that's what I'm going to use. So conservation of energy in this context looks like this. So it'll be initial potential energy plus initial kinetic energy equals final potential plus final kinetic. And our system is this stuff right here. We're going to ignore the presence of the Earth. Okay, maybe this happens on Earth. We're also going to assume that this macroscopic object remains in place despite the repulsive force of the proton, also a simplifying assumption. Okay, of course, if it's on Earth, the proton's going to bend just a little bit, but keep in mind that it's traveling at 1 million meters per second, so it's probably reasonable to ignore that deflection. Okay, so the potential energy associated with the electric force, which is the only force we're worried about here, is Q times big V. Okay, I got to be careful of capital and lowercase because capital is electric potential, and then Q, I'll use a subscript for that because there's two charges here, charge of the proton and charge of the macroscopic object. So charge times electric potential created by this object at the location of the proton. Okay, and then kinetic energy, just translational kinetic energy. So 1/2 mass of the proton times the initial velocity squared, and then kind of same idea, Q of the proton times big V final plus 1/2 mv squared. Okay, so there's a lot of symbols flying around. It's actually going to get a little worse, but eventually it'll simplify. So let's actually think about the simplifying assumption. At least one simplifying assumption. So distance of nearest possible approach, will come when the speed is equal to 0. So if it still had some speed, perhaps going towards that, if the proton was still moving, then perhaps it's still moving towards towards Q1, in which case it can get closer and we haven't reached our nearest approach. So we can be sure that we're at the nearest possible approach when we're at the turnaround point, when the velocity is instantaneously 0. So we can get rid of that. Okay, so that simplifies things a little bit. But we have a couple terms here that we don't know what they are. So I don't know the initial potential far away, and I don't know the final potential at its nearest approach. So what we do is we use the potential of a point charge. So this thing here is creating a potential, an electric potential, everywhere in the surrounding space. And we can use the formula for that. It's fairly straightforward. So I'll substitute in the formula for electric potential. So it's the electric constant, 8.99 times 10 to the 9th in SI units, times Q, and I'm calling this Q1, over R. It's going to be R initial. So I'm just using KQ over R for electric potential. And you might recognize this arrangement as the electric potential energy of a pair of point charges. Okay, I don't like to jump right to that. It's just an aesthetic preference for me. I like to think of it as charge times electric potential, and then here's your electric potential. But certainly jumping right to this is a perfectly valid approach here. Okay, initial kinetic energy, we'll just leave that alone. And then we'll throw in the similar formula, but instead of R initial, it'll be R final. Okay, so still quite a mess of symbols flying around. There's one more simplification that we can do before we do the algebra, and that is that the initial problem statement was that the proton was fired from very, very far away, so that means that R is very, very large, and so this whole term is going to go to 0. Okay, so R goes to infinity, and therefore the whole thing goes away. Okay, so then we get something that's at least not quite so bad, and at that point it is actually, let me go ahead and put K first so it's a little more familiar. So there's our symbolic solution, or not our symbolic solution, our equation before we derive our symbolic solution. So let's make sure we know enough in this equation in order to solve for what we want, which is this one right here. So we can look up the mass of the proton, the initial I gave to you. That's a constant we can look up. Charge of the proton is known, and then this charge was given. So two empirical values that you can look up. Let me make that B a little smaller, just to make sure we don't confuse it with potential. Okay, so last thing is to solve for R. So not too bad. I'm going to skip over a few algebra steps, but R final symbolically will be this. Okay, and then we can just throw in numbers into that formula. So give myself some space here. 2 times 8.99 times 10 to the 9th. Charge of a proton, 1.6 times 10 to the minus 19. Q1, 3 microcoulombs, so 3 times 10 to the minus 6 coulombs. Mass of the proton, 1.67 times 10 to the minus 27 kilograms. And then B initial, 1 million meters per second. And I square that. Okay, I throw that into my calculator, and our distance of nearest approach will be 5.17 meters. So actually a macroscopic distance. The proton isn't going to get super close to this charge. It's going to push it away before it gets too close. Okay, so that's it for today. Have a good day, and I'll see you next time.